So if we continue our example, we have to interpret the B0, the intercept, and B1, the slope, and B0 is negative 133.8097. Okay, and this means that if foot traffic equals 0, then sales equals negative 133,810. Okay. Which is obviously an extrapolation. Okay, and we have to look at the slope B1, and that would be plus, because it's upward sloping, more foot traffic implies more sales. It's plus 23.673, which means that if foot traffic goes up by, let's say, 1,000, then sales goes up by 23,673. Okay, and do the 5 simple regression model conditions hold? Well, we can look at number 1, and that would be linearity. And if we go back to the plot where we have our regression line and the data points, then we see that the regression line follows the data points quite snugly. And if we take the residuals versus the x variable, then we can't really find or decipher nonlinear pattern, which means that our model has been correctly specified regarding nonlinearity. So, is it linear? Yes. And the second one is confounding variable. So do we have confounding variables? We don't know, but for example, a confounding variable could be that if the level of competition let's say if level of competition is related to foot traffic, then we might have a confounding variable. Okay. And for example, the third one, are the residuals independent? And we can look at the residual plot again, and if we could see a pattern, for example, that there was kind of a seasonality in the residuals, then we would say no to this, but we can't really see a pattern in the residuals, so we have to say that they are independent. Yes. And the fourth condition, do the residuals have the same variance? Okay. Similar. And we can see here that we can, if we just take a band around the mean here, we see that the variance is not dependent on the x variable. So we have to say that they have the same variance. And the fifth condition is, do the residuals have a normal distribution? And we see here from the histogram that there is indeed like a bell-shaped curve or pattern here. So we are inclined to say that this is normally distributed. If instead of one hump there would be two humps or three humps, then we would say that this was not a normal distribution. Or if the tail was heavy on one side and narrow on the other side, then we would have a skewed distribution. But our distribution looks normal. Okay, so on to part C. Consider the following situations. Explain whether they violate the simple regression model of sales and foot traffic. If so, which SRM condition is violated? Okay, for part 1 here, Bucket Hansen shops located in busier areas, more foot traffic, also have better customer service. Okay, what kind of violation might this be? Well, if you look at the list here, if you have a different variable affecting the outcome and is correlated with the x, then you have a confounding variable. Okay, so this is number 2. So single I or 1, yes, means that, let's see, this violates condition 2, right? Because customer service might affect the sales, right? And 2, the variation in sales is lower in Bucket Hansen shops located in busier areas. Okay. Yeah. If we just draw a bit, if you have sales and foot traffic, and you have like a positive, relationship here. If the variation in busier areas, so these with a lot of foot traffic, they are busy and they have lower variation in sales. So for example, their dispersion in sales lies quite snugly around the regression line, whereas the sales for less busy areas has greater variation. Okay? For example, like this. This would then violate condition number 4 of similar variance in residuals, because the residuals for the less busy part of the regression would have a higher variation, okay, higher variance. So this violates number 4. And number 3, the effect of 1,000 increase in foot traffic on sales is larger in busier areas. Okay, let's just draw it. So this is X and this is Y. So if you have a large effect in a busy area and not so large in a less busy area, you see that the line is not linear, right? Because the slope for the busy area is larger than the slope for the less busy area. So this violates number 1, the linearity. Okay. So, why do we care about the simple regression model conditions? Well, actually, if all conditions hold, and these you can observe or you can think about them logically, like the omitted variable, condition number 2. If they hold, then your coefficients they are appropriate estimators of the unobserved parameters. Which means that you can use the information you get from B0 and B1, the coefficients, to say something about the population parameters, which you can't observe. And if all of these assumptions hold, then the sampling distribution of B0 and B1, they are approximately normal. Okay, and what does that mean? It means that now you know the normal distribution quite well. So if you know that something is normal distributed, then you can say something about the probability of that normal distribution, and where you can expect the true value of these parameters to lie. So, and it means that if you have these coefficients, you can use the t-distribution to say something about the distribution of the coefficient, and remember that the t-distribution looks like the normal distribution, but it's like flatter. Okay, there's more uncertainty in the t-distribution than the normal distribution. So for example, the normal distribution is this one. Okay, t and normal distribution. Okay, but the t-distribution goes to or resembles the normal distribution if the number of samples, which is as the number of samples goes to infinity. Okay, so for very large samples, the normal distribution can be used to make inferences about the parameters given the coefficients. Okay, so really the point here is that we want to say something or get some information about the parameters, the unobserved parameters, by looking at one sample from the population. So, which brings us to inference. And inference is just to answer questions. And what we want to what we want to do is to be able to say something about the relationship between x and y using our sample. Okay, because we want to make something useful by taking a sample and make inferences based on that. So, for example, is the observed relationship between x and y in the sample strong enough to conclude that it also holds in the population? Which means that are b0 and b1, the intercept and slope, different from 0. For example, we have discussed that if the slope is not different from 0, then you might as well use the average of y to predict y. And how can we use the sample statistics b0 and b1 to determine a plausible range of values for the intercept and slope of the population? So here we use sample statistics, the coefficients, to get a plausible range, remember that they are t-distributed or normal distributed, and then you can make a confidence interval for the intercept and the slope. And remember that whenever you talk about the coefficients or the parameters, you make a confidence interval, okay? But if you want to predict the value of y given a value of x using the regression line, then you're talking about a prediction interval. Because given the x, you are predicting the y, okay? So now we need the standard errors of the intercept and the slope, the standard errors of the coefficients. And the reason why the intercept and the slope have standard errors, it's because whenever you take a sample, you get a different result. Okay, you tend to get a different result. If you continue to get the same result, then there's usually something wrong. For example, when you throw a die 5 times and you take the average of that die, then you get a certain value. But if you do the experiment again, then most probably you get a different mean, right? And it's the same here, because you get different samples gives you different intercept and slope. Okay, so that's why we need to consider the standard error, for example, of the slope. And you see here that, let's see, I'm going to get up my cheat sheet. You have the standard error, or of the regression, and which is also called root mean squared error, or it can be the error or root MSE, mean squared error, like in Stata, root MSE. And n is the number of observations, and the S of x is just the standard, or the sample standard standard deviation of x. Okay, so by knowing these three numbers, you can actually calculate the standard error of your coefficient. And a smaller standard error means that your estimate for B1, the slope, is more precise. So for example, if you have a narrow distribution, you can make a confidence interval, for example a 95% confidence interval, whereas if you have a large standard error, then you would have to make a wider confidence interval to get a 95% chance of containing the true beta 1, the true slope. Okay, so when is the standard error smaller? Well, the standard error of the slope becomes smaller if the standard error of the regression is smaller. And if you think of like a regression line of x and y, and you have a regression line and you have a very little dispersion around the regression line, then you're quite certain about the slope, right? The standard error of the standard deviation of the residuals here, they are quite small. Whereas if the standard deviation of the residuals, or the root MSE, is large, then you really don't know, you're not that certain as of what kind or what is the slope of this regression. Okay, and if the number of observations increase, then the standard error, or the uncertainty of the slope, goes down, and that's because the more observations you have, the more information you have about the population. So the more observations you, well, that's a typo. You have, the more information you have, again, the same typo. About the population. Okay, and lastly, if the standard deviation of x increase, then the standard error of the slope goes down. And you might say that if you have some data points and you have very little dispersion of the x, then you really don't know where the slope is going. Whereas if you have a lot of dispersion in the x, you are more certain as to where the slope would be. Okay, and we also have a standard error of the intercept, which is not as important, but we're going to go through it now. It's more complicated, but if n is large, then use this. Okay? So what does it say? It says that the standard error, the uncertainty of the intercept, is dependent on the regression standard error, okay, which is the standard deviation of the residuals, and it's dependent on the number of observations and the mean value squared of the x variable, and the standard deviation or the variance of the x variable. So how can we interpret this? Well, if the standard error of the regression, which is the residuals, is lower, then you're more certain about the slope, and if you're more certain about the slope, then you're more certain about the intercept. Okay? And if you have more data points, then of course you get more information about the population, and you're more certain as to where the intercept might be. And something which needs more to be explained more is would be these last 2 points. The standard deviation of x, if this is higher, then you have more information about the slope, and you get a better estimate of the intercept, like this, and you get a regression line, which is similar to the interpretation of the effect of standard deviation of x on the slope, but here you have a term with the average value of x. If this is higher, then the standard error of the intercept is also higher. You can think of it as if your data points are close to the y-axis here, then you have a lot of information already as to where the intercept might be. Whereas if your data points are far away from the y-axis, then a tiny change in the slope might have large effect on the intercept. Okay. So, where do you find these? Well, in practice, you just tell the computer to calculate this. Okay. So, for example, if we continue our example, we have the number of observations, the n, which is 80 in our data set, and we have the root mean squared error of 150, and what we also have is the standard error of the slope, the b1, and we have the standard error of b0, the intercept. So here we have gotten the numbers from the statistics program, which can calculate this for us. Okay. So this would be the standard error of b0, the intercept, and this would be the standard error of b1, the slope. So that's all for today, and see you next time.